Okay, so now we're going to discuss the universe, right? The Milky Way is one of the galaxies made in our universe, of course, right? And in our galaxy at least. And in that galaxy, we have our own solar system. And in that solar system, we have in that galaxy, we have infinite solar systems, right? So just imagine that the diameter of Milky Way is around 100,000 light years and contains 800 billion or more stars. And if even half of these stars, if they have planets around them like our own solar system, right? Then just imagine how many solar systems exist just in our galaxy. And this is just one galaxy. There are 100 billion galaxies in the universe that we're still discovering every day, right? So, what does that mean? 100,000 light years. It means that if I wanted to go from one end of my galaxy, this is Milky Way, by the way, and probably this is our solar system, right? So, if we had to go from one end of the Milky Way to the other end, we would have to travel at least 100,000 light years. And we know that one light year is 9.15 in 9.0, I guess, right? 9 point into 10 to the power 15 meters. So just imagine how big this distance would be, right? So that is why we made this uniform, at least a convenient unit to represent larger distance, astronomical distances more conveniently, right? Okay, now this is very important. This is very, very important. This topic is known as the Doppler effect. You will find this in A levels physics first year, A1. What is the Doppler effect? You may have observed this in real life that sometimes, for example, if you are standing at this point, and you may try to do this in real life as well, if, for example, a car or an ambulance is trying to come close to you and they are using a speaker to produce a sound, let's say a horn or let's say an ambulance's alarm or anything, when they are coming close to you, they sound whatever they sound like, but when they walk away from you, it feels like that the sound changes, right? So have you ever experienced that? Just a, so the sound feels like it has changed. Now, the interesting part is that the source didn't do anything. It didn't change the horn midway, it didn't change the sound of the ambulance midway. But why do you hear it differently? You see, for a stationary observer, when you're standing at this point, if the car is moving towards you, its apparent frequency increases. When it's moving towards you, its frequency increases. For example, if it is producing a sound of 500 hertz, a constant 500 hertz, if it is moving close to you, this is the original, by the way, original sound of the horn, right? When it is approaching you, it looks like that it is actually 510 hertz. And we can also verify this using a CRO and an oscilloscope to find what the graph looks like. But when the object starts moving away from you, the frequency appears to reduce. And it probably could be at 485 hertz or 470 hertz. Depends on the speed of the object as it is moving away. Now remember, you are not moving from your position, the object is, right? So we remember and we find out that if the object, and we conclude basically that if the object from your perspective is moving away, its frequency decreases, and if the object is coming close to you, its frequency increases. You can explore its reason online on your own accord. The depth and why it happens is not required. That's a very entirely different discussion. But if you want to research on it, you can do it on your own, right? So this is the effect, or you can say this is the observation we have carried from the Doppler effect. But how does it help us in real life? What are we trying to look at? What are we analyzing about the universe that we are actually interested to know, right? Right now, we are, you can say, hell-bent on this theory that the Big Bang explosion took place and it actually caused the expansion of the universe or creation of the universe. Okay, fine, good. So the theory that supports that is the Big Bang theory or the Doppler effect or the Doppler shift. Actually, you can say it justifies that in some way. You see, what we did and what we observed in real life that actually gave us an intriguing situation. We analyzed the spectrum of the sun that is very close to us, our own sun, and we realized that this is what the sun is giving us. It's giving us some ultraviolet radiation, some visible light, and majority infrared radiation, which actually causes the heating of the earth and us and when we go into the sun. Visible light is only good enough to make us see the objects around us, and the ultraviolet is eventually very dangerous and causes cancer. So you will notice that the ozone layer reduces ultraviolet radiation much greater or much greatly than the visible light or than the infrared light. So it's not the responsibility of the ozone layer to reduce the radiation level, rather it actually acts against the UV radiations. It reduces the concentration greatly. So when we analyze this and we recognize that okay, these are the radiations or these are the wavelengths coming from the sun, so we should expect similar pattern from other stars which are away from us, right? So what we did, for the sake of example, this is where we're standing right now, and this is the color, this is the sun. To my eyes, it looks yellow. And of course, the color is subjective. You may say that as orange, some students say that as yellow. But for the sake of discussion, let's say that it's yellow. I know that my sun is not even coming close to me and it's not going away from me. So now I know that every star in the universe should look like to me as a yellow colored object, right? Okay, good. So, but in real life, when I'm standing at Earth, let's say, and I observe another star far away in the galaxy, it appears to me when its radiation reaches my eyes that it's actually red. But by the time we had also analyzed red supergiant as well, but that healthy sun or healthy star is red colored. Why is it red colored? You see, if I analyze the spectrum of the colors of the rainbow that we can see, of course, right? So the wavelength, let's go back. The wavelength of red color is 700 nanometers and the wavelength of blue color is 400 nanometers. We did that when we were doing electromagnetic spectrum, right? So according to V equals to F lambda, for red color, if my wavelength is high, its frequency is low. But for the blue color, frequency in lambda, if the lambda is low, then its frequency is high. Now, if I look at the spectrum closely and start from red and go to blue, red is 700, blue is 400, and yellow would be somewhere in the middle, right? Let's give it a value. For the sake of discussion, let's say that this is 600 nanometers, right? So if I go towards red, I am increasing the wavelength, but I am decreasing the frequency, right? But if I move towards the blue color, I am decreasing the wavelength, but I am increasing the frequency, right? So to our surprise, this is what our sun looks like. Our sun looks like to us as a yellow colored object or whatever wavelength that is, right? But when we analyzed the color of a distant star, you can say we were laid back a bit, that they appear to us as red colored. That would mean that their frequency is less. And how can anyone's frequency be less when it's a young star? So what's happening right now is that to my eyes, it is appearing to be red, although truly it is yellow because it's moving away from me. So if it's moving away, the wavelength that actually reaches me has a higher wavelength but a reduced frequency. That was justified using Doppler effect, right? So when I looked at another star, young star, that also to my eyes appeared to be red. But if this star was coming close to me or coming closer to my perspective, then the the frequency would have increased and the wavelength would have decreased. To my eyes, it would have looked like a blue colored object. In truth, it is yellow. but to me it would have been observed as a blue color, right? But all the stars, according to the universe and the galaxy, wherever I'm standing in the universe, right? Wherever I'm standing in the universe, this is where I'm standing right now. This is you, for example, and these are all the galaxies around me, right? All of their stars appear to me as red, which means that they are not coming close to me. They're actually moving away from me because only the object that is moving away from me, not the object but the star, will appear not yellow but red due to Doppler effect, right? So whenever we checked out any other galaxy around us, any other solar system around us, all their young stars appeared to be red. They gave out the impression of being red, which meant that the universe is expanding. This is the conclusion of the Big Bang Theory. That if all the galaxies and all the systems around me are moving away from me, then the universe is expanding. Okay, fine, no problem. Then how does it justify Big Bang Theory? Let's go back to the Doppler effect. Now, this diagram specifically is not a part of your course, right? You will strictly find this in A levels. But I like to discuss this with students because it clears out a perspective that is, you will find this word later in physics that is known as spectrum. This whole band is known as a spectrum. This graph can be called as the spectrum of the sun. Spectrum simply means that what are the wavelengths this object is emitting? What are the range of values that this object is emitting, right? So we must familiarize ourselves with the word spectrum. Okay, so for the sake of example, this yellow color is what I was supposed to see from every star in the galaxy if they are held in their own places. But what I see is generally a red color. Red color. Why? Because of the Doppler effect. If the frequency is decreasing, that means that from my location, that object is moving away. Right? This is what we discussed on this slide. This one. Right? Okay. So, if all the stars around me are appearing to be red, that means they are moving away from me. And if all of them are moving away from me, that means that there must have been a lifetime or some ages ago when all of these galaxies would have been located or be a part of a single object. This is where we actually came across, or this is what we actually conclude for the Big Bang Theory. That if, let's say, right now, we are observing everyone to be moving away from each other. Everyone is moving away from each other. It's an expanding universe. If they are moving right now, they must have started from an initial situation. They must have been present collectively as a single entity, as a single mass in their previous lifetime, right? So if we go, let's say the universe is 10 years old, for the sake of example. If we were to go back 10 years in the past, all of these would have actually started from somewhere. They would have been present at collectively at one location. So again, this is a theory. We haven't tested it. We can't test it. We are trying to test it. And we're trying to develop some equations and, of course, collecting data all the times. So this is just a theory right now. This is not a fact right now. Okay? Okay, so we argue that if everyone is expanding, everyone is moving away, then they should have been located at a single pivot or a point. So this gave us to the birth of the universe. This gave us the idea about the Big Bang Theory or the Big Bang explosion, which happened approximately 14 billion years ago, right? And now all the galaxies are moving away from each other. There is one extra point that I would like to add over here that you will find later is about the speed of recede. You see, this is also very interesting. If this is where I'm standing right now and I have a galaxy that is approximately at this distance from me, it is moving away from me at a certain speed. For the sake of example, let's say it is 500 light years away from me, and it is moving away from me at a speed of 3 kilometers per second. Okay, fine. If I have another galaxy around me at another location which is a bit farther away from me, let's say this distance is approximately 1500 light years, much farther away than this galaxy, right? Its speed would be approximately, let's say, 100 kilometers per second. So, as the galaxies are moving away, their speed is also increasing. So, they are accelerating as they are moving away from each other. So, whoever or whatever galaxy is closer to our galaxy has a lower speed. Whoever is at a farther distance is moving away at a greater speed. How do we know this? We know this by Doppler effect. You see, there are a few formulas for the Doppler effect. You will do that in A levels, that actually give us the value, that what is the actual frequency based on the speed of the object. The greater the speed of the object, the greater the change in frequency we will observe. For example, the original frequency is 500, and what we are getting is, let's say, 233 hertz. That means that the object is moving very, very fast, right? Because we are very far away from 500 hertz. So this is known as, in physics and terms, as speed of recede. They're running away from us, and as they're doing so, they are accelerating. And generally, this is actually known as Hubble's law. You'll get to that in A levels. But why is that happening? Why are they speeding up as they're moving away from each other? They're speeding up because the gravitational attraction on all the galaxies of each other is reducing, because they're moving away from each other. The gravitational attraction between them is decreasing. So eventually they're ending up accelerating away from each other, right? The Hubble's law, speed of recede, these are not a part of your course. This is just an extra point justifying Big Bang theory even further, right? So this is our chapter of space physics. Our syllabus